Welcome to Lecture 2. What we're going to do today is start building a mathematical framework around some of the ideas we saw in Lecture 1. Before I get into the detail of that, what I want to do is talk very briefly about just the rationale of coming up with mathematical frameworks in physics, because often what you see as an undergraduate is just the correct version of the mathematical framework, and very rarely do you see how we actually get to it. What I'm going to do today is start with a mathematical framework that basically treats quantum systems as residing in a complex vector space. And one of the questions that often comes up when I've taught this course in the past is, well, why a complex vector space? Why not a real vector space or something else? And this sort of comes down to this question of how we actually build mathematical frameworks that we don't talk about very much. And so probably my favorite example of where this sort of way of thinking comes from is Einstein's theory of special relativity. So you'll probably know from your first year courses that, you can take an object that's moving, it's a car accelerating or a car decelerating. We have these really nice equations that work really well. We can predict where the car's going to be at some time after an initial point if we know what the velocity and the acceleration is, for example, right? And what we find with that picture that we have there is that it works really, really well right up until the point where the velocity becomes close to the speed of light. And then all of a sudden, all of the predictions we make start being wrong. At that point, you basically have to start trying to build new mathematical models. And the way this often works is that you look at the observation of the system and you try to draw clues from that in terms of, how do I actually build a better model for describing that system, okay? And so more or less that's what happens with Einstein's theory of special relativity. Now you've got a sort of a more complicated version of normal mechanics that adequately describes both what happens when the speed becomes very, very large and close to the speed of light, and also what happens when the velocity is quite small, okay? Covers that entire range. And so now you've got a sort of a new, better theory that covers the old range and fixes the problems you had before. We're sort of doing the same thing here with quantum mechanics. We're basically saying, look, we've got these new behaviors, now we've got to build a model to do this. And when in physics, this happens all the time, it's just that where this is happening is so far advanced in the subject that as undergraduates you're not really seeing it going on. What you're seeing is, what came out as the winning theory 100 years ago. And so the way this happens is that basically a whole pile of different people will go away and come up with their ideas for how to handle this system. And then they will start testing their mathematical frameworks against what you see in the experiments. And of course, if your mathematical model starts getting lots of wrong answers about what's going, it doesn't last very long. If your mathematical model starts getting bits of the behaviors right, then more and more people go, oh, this is useful, I'm going to start using it. And you sort of push the envelope and eventually you kind of hope to get something that describes what's going on, okay? And so this is more or less the same in quantum mechanics. So if you go far enough back, you will see a variety of different approaches. There's two really notable ones. There's the one that's called the Schrödinger picture, where they try to basically say, let's have wave functions and use that to describe sort of the interference nature of quantum mechanical systems. And then you can see another one that you might not have heard of called the Heisenberg picture, or the matrix mechanics picture, which is basically, let's try to describe these systems from the perspective of linear algebra and vector spaces and see if we can describe those systems that way. Okay, now both of those theories are reasonably successful, and so that's why they've lasted right up until this day. And as with all things, you have some people who like one version better than the other, and sometimes one works better for one type of problem than works for the other one. Now the interesting thing about quantum mechanics is that ultimately, if you stick around in the subject long enough, what you end up doing is using a mishmash of the two, interchangeably depending on what sort of type of problem you've got. And that means that often the subject's taught from one of the two and then you try to pick up the other one on the way, okay? I'm going to try and move from one but move across to merging the two very, very quickly in my part of the course, so you get to this point of having sort of a combined theory relatively quickly and don't get caught up in having to learn all the intricacies of one and then go back and learn all the intricacies of another, and then drop most of the pieces and join the bits in the middle. Okay, so this is where I'm going to deviate from Griffiths a little bit. Griffiths likes to define lots and lots of things related to linear algebra, idempotent and all this sort of stuff. It's not very useful when you're doing quantum mechanics. I'm really going to try and focus down on the stuff that's useful so that we can get to a useful package as quickly as possible. The other question often comes up is, well, why a complex vector space? Why not use a real vector space? And the answer to that is, well, you can try that. You can try using a real vector space. And what you find is that the mathematical framework doesn't describe all the behaviors. So obviously that's not good enough. You need to add something to it. And so one way to add something to it is to enable complex numbers. And then what you find is actually that space describes all the behaviors in here. Okay, so ultimately what you're going to read in the books, it's going to look like, oh, you know, Joe Bloggs has come in and developed a theory for quantum mechanics, and he's a genius because this theory works for this. The reality is actually kind of quite different, that there's a whole pile of Joe Bloggses out there who see some interesting system they want to describe, and they all go off and try and work out their ways of doing it, and then there's lots and lots and lots of wrong things on the way, and eventually the right things sort of filter their way out and merge their way in together to build you up a theoretical picture. Okay, so all right, so let's kick off with a summary from the last lecture. So we'll go to some slides, and probably the top points from lecture 1 will be, what we're going to do here is focus on the simplest possible system we can deal with from a quantum mechanical perspective. And that is basically a thing that we're going to call a quantum spin, and it's simply an angular momentum with two possible states as outcomes of a measurement, a +1 and a -1. We might call them other things here and there, but generally there's two states, okay? And often if you're looking through writing about quantum mechanics, you'll see there's sometimes called the two-state system or two-state problems. The other thing that we found in the first lecture, and this is important to the framework, mathematical framework we're going to build up, because we have to be able to deal with these issues. The quantum measurement has three characteristics. It's invasive, it's probabilistic, and it's typically quantized. Okay, and what that means is, invasive is that when you do a measurement, that measurement can affect the state of the system in such a way that you kind of have to disconnect measurement from states because they're not necessarily the same thing all the time. Measurements in quantum mechanics are probabilistic, so you can do a particular measurement and you can get a different outcome on each repeat, and it's not necessarily because the instrument's doing something wrong, it's because of the nature of quantum mechanical systems. And often what you have to do is do large numbers of repeated measurements in order to extract the behaviors, because there's a probability aspect to it, and that requires statistics. And the last one is that the outcomes of measurements in quantum mechanical systems are typically quantized. And what that means is that every possible outcome is not necessarily available to you. And if we think back to yesterday with a spinning object like a football in classical physics, the angular momentum can have any magnitude it wants, and it can have any direction it wants, right? And the thing we saw when we came down to sort of a basic quantum mechanical object like a spinning electron is that it has only one allowed total angular momentum, and the angular momentum component along the z-axis can only be one of two possibilities. It's either pointing upwards along that z-axis or it's pointing against that z-axis, okay? And so that's what I mean by quantized. Instead of being there an infinite number of possibilities, there's some finite number of possibilities, 2, 5, whatever it is for that system, okay? And then the last point, which I didn't really make explicitly yesterday, but if you look back on it, you'll see that it's sort of riding through, is that for classical systems, the states, or the space of states for a system is a set. Let's imagine that I've just got a box with a gas in it and I want to know what the temperature is as a function of time. What I would do is measure the temperature, write down the number, measure the temperature, write down the number, and do this time and time again, just like you do in your undergraduate labs, right? That's a set, right? Sequence of numbers in a string is just a set. And so for classical systems, generally what we can do is describe the states of the system as a set of numbers that describe the state of the system. The other thing that we find for classical systems is that Boolean logic works. We can ask questions like and or, and we can do, we can think about what a not means and stuff like that, okay? what we'll see going forwards is for a quantum system, the space of states is a vector space, right? So now what we're doing, instead of taking a series of scalar numbers, what we're doing is actually looking at a space that's full of vectors. So we actually have to add something to it, not just a sort of a magnitude, but also a direction. And the other thing that we saw yesterday is that Boolean logic fails for quantum systems. And that means that if we want to do something useful with them from an information perspective, we sort of need to come up with new systems of logic. I won't have time to fit that into the formal part of the course, but I'll give an optional lecture on the end where we talk a little bit about logic for quantum systems, just for everyone's curiosity. Okay, so let's get started with this idea of states of systems for quantum mechanical systems being represented as vectors, okay? So in the first lecture, what we did was we looked at quantum spin, measure it with an apparatus that basically has a preferred axis using a magnetic field, and we look at what the angular momentum component relative to that axis is, because there's two possibilities. Either it's aligned with that axis or it's anti-aligned with that axis, the +1 and the -1, okay? And so you can imagine if we have an analysis axis along Z, the two outcomes, +1 and -1, correspond to sort of a spin up along Z and a spin down along Z. So if you look down here, you can think for a moment in terms of real space as an up and a down, right? And that makes perfect sense. We're thinking in a 3D XYZ world, and we're now thinking about, you know, what the alignment of the magnetic moment or the axis of our angular momentum is relative to that 3D world, okay? Going forwards for this course, I'm going to call those two possibilities, the +1 and the -1, up and down. And at the moment, you'll say, what are these funny brackets, the straight line and the angle bracket on the right-hand side? In the second half of this lecture, I'll explain exactly what's happening with the notation there, right? For now, just accept that they come as baggage with the up and the down. If you look through different textbooks, you will all find them describing this version of quantum mechanics in terms of up and down, spin up, spin down. But often they will have different notations for it. So sometimes they will use up and down arrows. Sometimes they will use just plus and minus, getting rid of the 1 because we know that it's a 1. Sometimes they will use +1 and -1. They will always use this straight line angle bracket notation, which I'll explain in the second half. It's a convention in quantum mechanics, okay? Now, we're interested in up and down, and most textbooks will just talk about up and down, but you'll remember from yesterday, we can take our Stern-Gerlach apparatus and we can orientate that magnetic field any way we like in space, right? And so you'll remember we often ask the question about, is the spin aligned along the Z-axis? And usually we care about Z because we have a preference for choosing Z in quantum mechanics. It's just one of those things, you have to have a convention, so you have a convention, and basically everyone likes to choose Z as the primary axis. But you might want to look at, you know, what's the alignment of the spin along the X direction. You remember we did this in our sort of Qtron experiments yesterday. And there you can define two possible outcomes, right? Either it's aligned along X or it's anti-aligned along X. And that would be the equivalent of pointing to the right or pointing to the left. So what we're going to allow here is two other states, which I'll call L and R, and they basically correspond to a measurement in the X direction, finding the outcome being the spin points along right or the spin points along left, okay? Again, it's the same measurement. We get a +1 or a -1. Now we're just thinking in the X direction. And then to fully canvas the fact that we live in a three-dimensional world, I'm going to allow two more states, which is the measurement in Y, right? So you remember yesterday we looked at X, we looked at Z, we looked at X, and we never really cared about the Y direction. But you could do that. You could take your Stern-Gerlach apparatus and just rotate it by another 90 degrees and get it to go into the Y direction. And then what you'd be measuring is a +1 and a -1 in the Y direction. And what I'm going to do, because we often represent 3D space as in a 2D plane, is consider these to be into the page and out of the page as a pair of distinct states, okay? Now, I can take a single spin And because I live in a 3D world, I can have it point in any of these particular directions depending on which way I do my measurement, right? So all of these states are validly allowed. And if we're building a proper mathematical framework, we should be able to cope with all of those as possible outcomes, okay? The up and the down are easy. The left and the right are easy. The in and the out, we often don't really deal with very much. And the reason why we don't deal with them very much is because they take a little bit too much time, because this is the place where we end up having to extend into the complex vector space. We start having eyes turn up and things get a little bit more complicated. So I'll give you some examples as we go through the course where you can play around with I and O, but as a general rule, I'm not going to do it because it takes more time than doing L and R, and I've got limited time to talk to you in lectures. Okay, so at this point, I'm going to give you a very, very, very big warning. And if there's one thing you should take away from this half of the lecture, this will be it. The vector spaces we're going to talk about for dealing with a mathematical framework for quantum mechanics are decoupled from the system's real physical space, okay? So what we're going to do in a moment is start dealing with vector spaces. And the vector spaces are going to be built in axes where the axes are the two states that you can measure for the system. For example, up and down. That vector space is a separate mathematical thing to the real space that we're living in, okay? So the real space we're living in is these diagrams down here. The vector space that we're going to be working in to build sort of our mathematical framework for quantum mechanics is going to be a separate vector space, okay? What that means is that if you think in terms of real space, you'll get trapped very quickly. You have to keep these two things separate. The other thing is that these two spaces that we have typically very different dimensions to them. The real space that we live in is always 3D, and it is always real, okay? There's no complex components to it. It's just an X, Y, Z 3D space fixed no matter what you're dealing with. The vector space that we're going to introduce in the moment is always a complex vector space, always. And the number of dimensions it has is equal to the possible measured outcomes of a measurement that you have. So for our simple quantum spin system, there's two outcomes, up and down, for a measurement, or +1 and -1 for a measurement, no matter which direction you do it in. And that means that we're going to have a 2D complex vector space. You can imagine having a system that has a larger number of outcomes. Maybe think to it for a second to sort of the orbital angular momentum we talked about yesterday where we had 5. Then you would have a 5D complex vector space to deal with, okay? This real space is still 3D, but for that orbital angular momentum, you're now dealing with a 5D space. So you've got to think about two spaces, and the important one is not the real space. Just so I'm really clear in this, and I don't do it very often, if I go back to talking about my sort of real space vectors, I will call them 3 vectors because they're always 3-dimensional space, okay? Otherwise, if I'm talking about general vectors in this course, I'm referring to vectors in this complex vector space that we do quantum mechanics in. So typically this complex vector space we deal with in quantum mechanics is a thing that we call a Hilbert space. And if you look in the books, Griffiths, for example, you'll see all these really complex definitions for exactly what a Hilbert space is. And I'll let you go into those in mathematics. What I really care about here is what we can use. And so I'm basically just going to drill this down to the simplest possibility, which is for our quantum spin system, we're going to have a Hilbert space. And that Hilbert space is just going to be a simple 2D vector space. But it's a complex vector space, okay? So what we're actually doing here is underrepresenting the real nature of the space in any of the diagrams I'm drawing, because inevitably a page like this is really a 2D real space, and the Hilbert space itself is complex. And that explains another reason why, if I just pop back here for a moment, we like to deal with these two and we don't like to deal with this one very much. It's because these ones, the vectors we can write here, are real, and so they work with that 2D real representation of the 2D complex vector space. As soon as you get to these ones, the vectors start to get complex, and so presenting them on a diagram that looks like this on a PowerPoint slide basically becomes impossible, okay? All right, so what I'm going to do to start out with here is consider 4 really simple vectors in this space, okay? The first 2 are up and down, and what I really commonly do in these vector spaces, and this is one of the things that you'll see running through the books, is often we will give them the this Greek letter chi rather than the Greek letter psi, okay? Usually we use chi for spin and psi for spatial wave functions. Later on we'll merge that notation and sort of blur it a little bit, okay? So I'll just use this for now. Okay, so we have 2 really obvious vectors in this 2D complex vector space. They are up and down, right? And the first thing that you'll notice here is that I've set them as the orthogonal coordinates for that vector space, okay? These are what we'll call basis states, and in the second half of this lecture I'll actually go and formally define my basis states properly, okay? At the moment I'm just trying to give you a picture of what this is going to look like. What we'll normally do is make sure that these 2 vectors have unit length and live inside sort of this dotted unit circle that we draw in here, okay? And you can imagine this to essentially be sort of a sphere or a hypersphere in our 2D complex vector space, or our n-dimensional complex vector space, right? It's basically a unit sphere that has all the vectors inside of it. And the reason why we like to make that a unit sphere is because you'll remember we talked about quantum mechanics being probabilistic. When we calculate probabilities always add up to 1, right? You know, if I flip a coin, I've got a probability of a half that I'll get a heads and a probability of a half that I'll get a tails. And the total probability of anything happening is 1. And the probability of something happening being 2 makes no sense at all, right? Here, what we're doing is this idea of building up a mathematical framework. We want to be able to have something that enables us to explain how we get outcomes, up and down, and how we get the probabilities of those outcomes. And so what we want to do is build probability into this mathematical framework. And the way we're doing that is basically building probability in as the magnitude of the vector. And by restricting the magnitude of that vector to 1, we make sure it ends up being a probability that makes sense, okay? All right, so we've got these 2 vectors. We'll call them a basis, and I'll define that in the second half of the lecture. Then you can see in this 2D complex vector space that we can have more vectors, right? To give you 2 examples of them, you could imagine having some arbitrary vector here, the green chi. And the green chi is basically just the vector sum of a little bit of up and a little bit of down. And you can of course see that in here. So this is basically an up vector plus a down vector. We'll give you something in between. And then what we do is we put a 1 over square root 2 in here, and that's basically just normalizing the length of the vector so that it has unit length, okay? So what we do is make sure that this vector touches the edge of this unit circle. I'll talk about how we convert that into the probability of getting an up or a down in the next lecture, okay? So we'll come back to that idea. You can have up plus down as a possibility in this vector space now, and you can have up minus down as a possible vector in here. And so you can see, you know, if you take up and you add minus down to it, you would end up with a vector that points along here. Sure enough, you can normalize this thing and get a state that comes along in here, okay? What are these 2 states? These 2 states basically are what we call a superposition or a linear combination of the basis states. And so the best way to think about this for a moment is, you'll remember when we did the Qtron yesterday, we had this idea right in the first measurement that we had a spin pointing in some arbitrary direction. It wasn't quite up and it definitely wasn't down. It was somewhere a little bit off, right? And when it comes in, we do a measurement and we find either that it's up or that it's down, okay? And that initial state of not quite being up and not quite being down, we could imagine to be a little bit of up and a little bit of down mixed together in some way, okay? And that's basically what these superposition states are. Now, you could imagine that I don't just have one of these possible things that's not quite up and not quite down, but somewhere in between, and there'd be a whole pile of them. And sure enough, in this complex vector space, there are a whole pile of these possible superposition vectors, okay? Now, what we have to do here is basically generalize the magnitude of the amount of up and the amount of down. And so if you think back to here, the green chi and the orange chi, for example, what I'm basically doing is taking a 50-50 mix of up and down, right? I'm adding just as much up as I am adding down, get them together, and that gives me that vector in between. You could imagine that this might be, a vector pointing to the right, or a spin pointing to the right, it's a half up and half down. And what we'll show as we get through the lectures is actually this is left and this is right, okay? Hiding away in here. But you could imagine some state that's in between. It's a little bit more up than down, and if we do our Qtron measurement yesterday and take this spin, most of the time we would measure up, and it's very rare that we measure down, okay? And sure enough, that vector looks a little bit like this one. And so instead of having a half and a half, which when you do the numbers to make them make the vector have the length for the unit circle becomes 1 over root 2 and 1 over root 2, what you have here is basically two prefactors that are allowed variables, and you set them up such that the sum of the squares of them is equal to 1, okay? Now, there's a subtlety in here, which is that both alpha u and alpha d here are not just real numbers, but they can be complex numbers, okay? And so that accounts for the fact that not just do we have the possibility that, for example, right is a little bit of up and a little bit of down, but into the page is also half up and half down, and we need to be able to distinguish between into the page and left. And the way we do that is by enabling our complex plane, okay? So if we come back to the idea that we had at the start, if we make this vector space, our Hilbert space, just a 2D real vector space, what will happen is that the mathematical framework we have works perfectly good for up and down, and it works okay for left and right as well. And then as soon as we decide, hey, we live in a 3D space and we need to go into the page as well, the mathematics breaks down, right? There's not enough room in our mathematical framework to handle that extra third dimension. And this ultimately is why we have to deal with complex vector spaces for our sort of mathematical framework for quantum mechanics. We need to be able to have enough space in the vector space to be able to handle all the possible outcomes that happen from a sort of 3D real world perspective, okay? This is something that we call normalization, and I'll talk about that a little bit more in the second half as well. Okay, so just before I finish in this half of the lecture, one thing I want to point out is that at the moment you're probably thinking, oh, these 2D complex vector spaces are very, very hard to visualize. And the answer to that is yes, I absolutely agree with you. And my suggestion is that beyond the simplest possible cases, visualization is futile and you shouldn't do it, okay? To give you an example for this, what I'm going to introduce is a nice little model system now. It'll pop up once a couple of times during the course just to reinforce the fact that, quantum mechanical systems are more than just up and down. I'm going to have a thing that I call a quantum dice. And so if you think back to our spin yesterday, it's like a quantum coin, for example, where you've got two possible outcomes, a heads or a tails with 50% probability, right? And that's what we call a two-state system. There's quantized output, there's two possible outputs. Imagine we had a thing called a quantum dice. It would be a really cool thing to have, actually. And what it does is it has 6 possible outcomes, 1, 2, 3, 4, 5, 6. Each of those have a probability of 1/6 of occurring because we need the probability to add up to 1. And so there's 6 possible states. And what we have to do in our complex vector space now is deal with the fact that we can have 6 possible measurement outcomes, which would mean that we're really dealing with a 6-dimensional complex vector space. All right? You can build a problem like this. You can do quantum mechanics for it. It's kind of fun. It gets very, very mathematically detailed very quickly. But visualization is nasty. your first state, you know, the probability of getting 1 you can deal with. You can draw that on a page and go, all right, I've got a axis that corresponds to my outcome being a 1 when I roll my quantum dice. I could use my second axis for the state 2. I could use even my third one for the state 3 and try to just ignore the fact that there's complex numbers in here and what I'm really dealing with is real numbers. But as soon as I try to get the fourth state in there, I don't know about you folks, but my head explodes and there's no way I'm getting to 6, okay? And that's before I even start thinking about the complex numbers. With quantum mechanics, often we'll deal with that really simple system of up, down, left, right, simply because it's the simplest possible case that we can still fit into a 3D visualization. We can basically go, I've got a up, I've got a down, left and right will turn up in that plane because I can ignore complexes. As soon as I have to bring in and out, then I can't visualize the problem anymore on a page. And then you scale up to bigger systems where you've got 6 dimensions, you're gone. And if you go to the limit that we will take later in the course, where we start to deal with, you know, particle moving along a line with a momentum p, in principle you've got an infinite number of possible states, which is an infinite number of dimensions, and so you've essentially got an infinite dimensional complex vector space. There's no way you're visualizing that, okay? So possibly one warning to take forward here is to try not to get too deep into trying to visualize the Hilbert spaces beyond what we do with the simple up, down, left, right in this system. Often it's better to learn how to connect the really simple visualizations to the mathematics and then rely on the mathematics without the visualizations for there, right? It's a little bit like riding a bicycle with training wheels. The 2D complex vector spaces we show for a Hilbert space are like the training wheels when you're just starting to learn how to ride the bike, which is to handle all the equations. And then once you get good at it, you just forget about that and keep on going, okay? The visualization challenge that you have for quantum mechanics, it continues, and I'll talk a little bit about more about that in some of the other lectures. So let's take a break here. You might want to just have a think about some of the concepts in here, and then what I'll do in the second half of this lecture is actually get a little bit more formal about exactly how we're going to use this vector space. I'll see you soon.